Okay, for this video, I'm going to go over how to solve for different side lengths of a right triangle. So what I mean by that is, let's say we have a right triangle, okay? Sometimes we want to solve for A, and we know, let's say we know B and C. Give me one second here. Okay, sometimes we want to solve for A and we know B and C. Sometimes we want to solve for B and we know A and C. And sometimes we want to solve for C when we know A and B. Okay, so I'm going to go over how to solve for each of those. Essentially, for all of them, we're using the same principles. We're using inverse operations. Inverse operations, gonna talk really slow while I write this. Using inverse operations to isolate a specific variable. Okay, so basically we're just rearranging equations so that A is isolated if we're solving for A, or B is isolated if we're solving for B, or C is isolated on one side of the equation if we're solving for C. So let's go over a couple different examples, one of each. Let's start, actually no, I don't want to start with green because it's going to be like Christmas colors next to each other. Okay, example one. Example one, let's say that we have a right triangle and we don't know the hypotenuse. So we don't know side C if you're familiar with, the Pythagorean theorem. Now, if you're not familiar with Pythagorean theorem, quick review. Pythagorean theorem says that if we square side A and we add it to the square of side B, it'll actually equal the square of side C. Or if we're just trying to get C by itself, which is the end game, right? We would take the square root of that C squared and take the square root of that side, and we'd be left with, I don't know why it's being glitchy, square root of A squared plus B squared equals C. Okay, so there's Pythagorean theorem for you, which is also just distance formula in disguise, right? We're finding the distance between that point and that point. Okay, so let's go over examples. I know I already said that like 10 times. Okay, first example. We have a right triangle. We're going to call side A is going to be, that's a special looking 3. Side A is 3, side B is 4, and we don't know side C, so we're trying to find C. So I'm going to start with Pythagorean theorem. So I'm just going to write the formula out first. A squared plus B squared equals C squared. Now I'm going to replace the numbers that I do know into the equation. So I do know that A equals 3, so 3 squared. I also know that B equals 4, so 4 squared. But I don't know C, so we'll just leave that as C. Now the goal again is to get C by itself, but we'll just kind of forget about this for just a second, and I'm going to work on this side to simplify it. The first thing I'm going to do here, following order of operations, PEMDAS, the powerful PEMDAS. Okay, I'm gonna do the exponents first. So 3 squared gives us 9, 3 times 3. 4 squared, or 4 times 4, gives us 16. Again, still forgetting about this side for a second. Simplifying this, they're like terms, so we can combine them. 9 plus 16 gives us 25. 25 equals C squared. Now, this is not our answer because we want to get just C. We don't want C squared. To get C by itself, we're going to do the inverse of squaring something, which is the square root. And if you do it to one side, you have to do it to the other side of the equation. So, since these are inverse operations, they cancel each other out and we're left with C on this side. And then 25, the square root of that, is going to be 5. So we are left with C equals 5. Okay, so that's probably the most familiar problem with Pythagorean theorem, is just solving for the hypotenuse, right? But let's Let's do another example where we're solving for A and then one where we're solving for B. Okay. So let's say we have another right triangle and we don't know A. Let's say we don't know A. We know that B is 4 though, and we know that C is 5. And you're like, yeah, we already know what A is because you just did this problem. Just pretend that you didn't hear the last problem, okay? I want to demonstrate that these all work together. Okay, so first thing I'm going to do is rewrite the Pythagorean theorem. A squared plus B squared. This is just so I know what I'm doing, know where to replace what numbers. Again, we replace the numbers that we do know for the variables. So we don't know A, so we'll leave that as A. We do know B is 4. And we do know C is 5. Now, first thing I'm going to do is simplify the numbers that we do know. So I'm going to square those two. Again, we don't know A, so we can't really square it. But we can do 4 times 4, gives us 16. And we can do 5 times 5, which gives us 25. Okay. Now, we want to get this A term by itself. So to do that, we need to get rid of this 16. We don't want it here. We want to move it to the other side. We're going to do that using the inverse operation. Since it's being added right now, we're going to subtract it. And if we subtract from one side, got to keep the balance in the force, Luke, and subtract it from the other side. So those two cancel out. 16 minus 16 is just 0. We're left with A squared over here. And 25 minus 16 gives us 9. Now, we're not done yet. Again, we want to get A by itself, right? A by itself. We don't want A squared. So we do the inverse operation here. Take the square root. If you do it to one side, do it to the other. Square root of A squared, those two just cancel out. So we're left with just A. And then the square root of 9 is going to be 3. So now we have the same exact answers we did for our last problem, 3, 4, and 5. Okay, where is it? There we go. Same answers, 3, 4, and 5, even though we were solving for a different one. Okay. My dog just busted into the room. Hi, bud. Okay. Last example. So on this one, sorry, bud, locking you out again. Don't mind me. Last example. You just broke into the room again. Can't keep him out. Okay, right triangle. This case again, we're gonna know this time that A equals 3. But this time we don't know B. We do know C, however. So, first step, I'm gonna write the Pythagorean theorem out. A squared plus B squared equals C squared. You're like, yeah, I get it. I get the hang of this now. But I'm going to do an example just in case there's a few people who want another example. I know you're out there. Okay. Again, I'm going to replace the numbers that I do know. So I know that A is 3. I don't know B, so I'm going to leave it as B. I do know C, though. C is 5. Okay. Again, I'm going to simplify the numbers that I do know. So 3 times 3, 3 squared, gives us 9. Still don't know B, so can't do anything there. And then 5 times 5, or 5 squared, gives us 25. All right. Again, we want to get this B term by itself, so we need to get rid of this 9. Because it's positive, we're going to subtract it. Right, we're doing the opposite. So 9 minus 9 gives us 0. So we're left with B squared over here. Just realized I'm saying so a lot. Okay. B squared equals 25 minus 9, which gives us 16. Now again, we still need to do more because we need B by itself, not B squared. So we're going to do the opposite. Take the square root of both sides. The square and the square root cancel each other out, and we're left with B equals 4. So we solved for all 3 all three, and each time we got the same answer. We have a 3, 4, 5 triangle. 3, 4, and 5. Up here, 3, 4, and 5, even though we were solving for different variables, right? So that's proving to you that using the Pythagorean theorem, no matter which variable we're solving for, A, B, or C, we get the same answers, right? You could check your work and make sure it works. That was really redundant. Okay, hope that helps you guys.